Okay, so here we have a graph of position versus time, and we want to turn it into a velocity versus time graph. So we want to remember that a position to velocity is the derivative, which is a slope of a position graph, gives us the velocity. So we can look at areas of slope to get the velocity during those same time points. All right, so between 0 and 2 seconds, the object is moving at a steady rate, represented by a linear sloping line on our position versus time graph. So we know with a straight line, that's a single slope value, we know that the velocity is constant. So we can use that to move that velocity graph, or position graphics rather, down to the velocity graph. This object is moving 1 second, 1 meter, 2 seconds, another meter. So it's moving at 1 meter per second. The velocity is positive. This slope is positive. So if I were to represent that on the velocity graph, over the course of the first 2 seconds, we are moving at a constant positive 1 meter per second. Well, then what happens right at 2 seconds? Well, we move 1, 2, 3, 4, 5 meters from 2 to -3 in 1 second. 5 meters in 1 second. We're in the negative direction, a negative slope, so that's a negative velocity, and it's constant during this time period. So from the period between 2 and 3 seconds, I have a steady slope, constant velocity, it's a negative slope, negative velocity, and it's at a value of -5. So at 2 seconds, we instantly go to -5 for that second, between 2 and 3 seconds. And then what happens? Well, the position just hangs out here at -3 meters for 2 seconds, between 3 and 5 seconds. If it's not moving, then the slope is 0. The velocity is 0. We're not changing position. So at 3 seconds, our velocity goes to 0. Then between 5 and 6 seconds, we're moving in the rightward direction. We're going from -3 to -2 in 1 second. That's 1 meter in 1 second. It's a positive slope, positive velocity. We can see that rightward motion, and we're back to 1 meter per second. We don't know what happens at 6 seconds. The graph stops there, but we can represent this entire position time graph using the slopes to get our velocity versus time graph. Now the second part of the question asks, what is the acceleration at a value of 2? Well, this is where we get an instantaneous change in the motion of the object. If I were to look at the slope right at this instantaneous change, it would be infinite, undefined. And so I can't say anything about the acceleration at that point. Now in real life, we know that that doesn't happen, right? If I'm going to change direction, I have to slow down, come to a stop, turn around, and then speed back up till I get to my new steady velocity. But based on this picture itself, we have an instantaneous change, an undefined slope, and therefore we can't say anything about that acceleration. All right, so position to time graphs, we look at the slope of the position to get our velocity time graph, and we can calculate those exact slopes given the numbers in this particular example. Remembering positive slopes, positive velocity moving to the right, negative slopes, negative velocities moving to the left, and when we don't have any motion, we get a slope of 0 that was represented on the origin of our velocity time graph. Good job.